different concepts related to astrophysics. Good. Yeah, for people who want to swap their notes, I'll give you 2 minutes time. You can take your notes. It is Science and Tech class today. I repeat. I hope the video and audio is clear. If there is any issue, you can drop a message. Can we start? Where did we stop the last class? Did we finish with Project Netra, if I'm not wrong? Am I correct? Can someone reply in the message? The last topic that we discussed was Project Netra, a space situational awareness program by ISRO. Is it correct? Based on ground-based telescopes and different methodologies, we'll be looking for space debris. So the satellites will be making collision avoidance maneuvers. That is what we finished with. Am I correct? Can someone confirm this? People present in the meeting, can someone reply? Look at your notes and tell me, did we finish Project Netra? Yes, okay. Good. All right, good. So I'll just give you a quick revision for with respect to whatever we dealt in the last class. So initially we were dealing with three things. One was Antrix Corporation. I told Antrix Corporation is a private and a commercial wing of ISRO, and it mainly concentrates on international markets. And then about next one was New Space India Limited. So this is newly established in 2019. This is launched with respect to commercial activities inside India. So more like increased private participation in the field of space science. And then we were talking about a regulator called InSpace. It's an autonomous body under the Department of Space, where different people from Prime Minister's office and everyone will be constituent of this body. Good. Hold on. Thambi oru nishamga. இந்த லைட் ஆஃப் பண்ண முடியுமா? இங்க glare அடிக்குது போர்ட்ல. இது மட்டும் ஆஃப் பண்ணிடுங்க. About 3 organizations, and after that we were talking about India's indigenous navigation system, that is IRNSS, India's Regional Navigation Satellite System, also called as NAVIC, Navigation of Indian Constellation. So we were discussing about this one. இந்த சைடு தான் ஆஃப் பண்ணணும். இங்க பாருங்க, இந்த கார்னர்ல தெரியுது. அந்த சைடு இருந்தா ஓகே. எங்க இருந்து வருது இந்த லைட்? அப்போ இதுதான் இது ஆஃப் பண்ணுங்க. இல்லை இது அந்த ஷேடுன்னு நினைக்கிறேன், விண்டோ ஷேடு. முடியுமா அது? சரி. Hold on, we have a small gap here. You people might find it difficult to read. Hold on till we fix this. Yeah, better now. Good. Okay. So IRNSS, it has around 7 satellites, 4 in geostationary Earth orbit, and 3 in geostationary Earth orbit, and 4 in geosynchronous orbit. So I told you about other navigation systems also. I told you it is Beidou, that is a satellite system of navigation system of China, and then we have GPS, Global Positioning System by USA, and then we were talking about GLONASS, which is owned by Russia. Good. And then Galileo, that is owned by European Space Agency. Now, I also told IRNSS is included as a part of International Maritime Organization's radio network. These are some of the important concepts which we discussed in the last class, if you could look at your notes. And then we were discussing about Gagan. So Gagan is basically, it's an augmentation of GPS. So it uses the same system GPS, but we are improving the accuracy of GPS, predominantly used for aerospace industry, aeronautical industry. And then also it's used for other purposes like for increased accuracy of GPS in the field of forestry management and other purposes. I told you it can achieve accuracy of up to 7.6 meters. Good. And then we were talking about the next thing, that is Gemini. So it's a Marinus instrument, Gemini. So Gemini is basically a one-way broadcasting device. So if the fishermen have this Gemini device along with a mobile phone with a good Bluetooth, so we can send them message about cyclones, about potential fishing zones and everything to them through the Gemini device. It's a one-way radio broadcast device, and it uses the satellites. Good. And then next thing we were talking about Gaganyaan. That is upcoming India's manned mission. It's called as Gaganyaan. We'll be sending astronauts to the space. They'll be orbiting the Earth, and then they'll be returning in 1 week. So when we were talking about Gaganyaan, I told you one more concept that's called as half humanoid robot. That is Vyomitra. And then we discussed about other similar humanoid robots that were sent to the space, including Fedor and other robots by different countries. And then we were talking about different satellite systems of India, classified into two main types. One was communication satellite, the other one was Earth observation satellites. So what is Earth observation satellites? Mostly the remote sensing satellites and satellites that's used for surveillance purposes. Those are called as Earth observation satellites. And then communication satellite, I told you INSAT, GSAT, and everything. So these were the concepts which we were discussing in the last class. And then Project Netra was for space situational awareness. Good. So the next concept is small satellite launch vehicle, SSLV. Repeat, it's called as small satellite launch vehicle. First question, what is meant by a small satellite launch vehicle? So as the name itself says, it's going to be a smaller vehicle that will be of sub 110 ton. I repeat, the total liftoff mass will be less than 110 tons. Compared to the conventional rocket that is more bulkier, this is going to be just 110 ton rocket. That's fact number one. And fact number two, why India is pushing towards SSLV, small satellite launch vehicles means, see, we are concentrating towards space trade. So we want to launch other satellites. We want to give low-cost access to space. That's a keyword for small satellite launch vehicles. You can use it in your mains answer writing. Low-cost access to space. So till now we have been launching using PSLV and GSLV, which consumes a lot of fuel. And SSLV, it will be sub 110 ton. It will take less than a week, around 7 days to assemble. These data are not necessary. I'm saying for understanding. See, generally a normal PSLV or GSLV, it will take at least 70 plus day to assemble. So if you want to assemble the entire launch vehicle along with the satellites and everything, it's going to take more than 2 months, basically 70 plus days. But if you see small satellite launch vehicles, it will take just 7 days and much lesser people to assemble. And also we can launch more satellites. Good. So we are providing low cost access to space, which it will promote international trade also, space trade. And most importantly, small satellite launch vehicle, it can launch satellites only to low Earth orbit, important. It cannot launch satellites to high Earth orbit. It cannot launch to medium Earth orbit. It can launch satellites or any payload to low Earth orbit, LEO. Good. Now coming to the challenges that we will face with respect to small satellite launch vehicle. See, right now ISRO is searching for a second launch port. So let's assemble this is assigned. Assume this is India and we have Sri Lanka here. What happens is whenever we launch rocket from Sriharikota, see observe, whenever we launch rocket from Sriharikota, and if you want to put it in a polar orbit, we do not shift the rocket immediately. So what we do is we generally launch it in a slanting way. We travel to certain distance before taking a detour. The main reason is if there is a failure, so if there is any problem associated with the launch vehicle, if any firing is going to separate, or if the entire launch vehicle is going to collapse on the ground, it will fall on Sri Lanka. So what will happen? There will be a large-scale destruction, both in terms of property as well as lives. So to risk this, ISRO generally travels much higher distance than the projected distance. The trajectory goes like this. It travels much farther and then takes a path towards the polar orbits. So this is with respect to PSLV and GSLV, if you want to put in a low Earth orbit. Good. But the problem now is all the small satellite launch vehicles, SSLV, it is going to be sub 110 ton, which means we have to reduce the amount of fuel consumed and we have to reduce the distance traveled, which means we cannot take this path. It's going to consume more fuel and it's going to add up the overall mass of the launch vehicle. So what ISRO is planning to do is, it is planning to build one more launch port somewhere close to South India. Good. So the second launch port, for now, it has been finalized as Kulasekharapattnam. I repeat, it has been finalized as Kulasekharapattnam. It's located in town of Thoothukudi. It's located in Thoothukudi in Tamil Nadu. What the location's name is. Kulasekarapatnam. And now the problem associated with it. You can use it for constraints faced by government while implementing a project. Good. So one main problem associated with setting up a second launch port at Kulasekarapatnam in Tuticorin. One main constraint is this small satellite launch vehicle, the entire launch pad and everything, it's going to consume at least 2,000 hectares. At least 2,000 hectares of land is needed so that we can set up a launch facility and the associated labs and everything. Good. So which means the government has to acquire at least 2,000 hectares of land, which is going to be a momentous task. Because generally the southern Tamil Nadu, with respect to the recent happenings of the Sterlite protest and everything, people are in agitation mode or they're in a protest mode. So if ISRO is going to ask for around 2,000 hectares, which will include all the cultivation lands and everything, it's going to be a large problem. So keep a track on this issue. More developments are yet to come in. Good. That is with respect to small satellite launch vehicle. That is India's second spaceport. The main reason is to launch the small satellite launch vehicle, SSLV. Good. Coming to the next one. Any specific reason for choosing this space? Yeah, good question. See, if you place it here, it is parallel to Sri Lanka. So imagine the vehicle is launched from here. It can go directly in this direction. It can directly travel towards the polar orbit. So what will happen if there is a failure? At any cost, it won't fall on Sri Lanka because Kulasekarapatnam itself is parallel to Sri Lanka. Good. So we don't have to take this path. Instead, the satellite can be launched in this way, which is going to be much easier. So it is to make an easier maneuver and we can reduce the fuel consumed. That's the main reason for choosing it close to southern tip. Clear, ma'am? Is it clear? Why not Kanyakumari? Yeah, there are a lot of factors involved in it. So not only, there should be a lot of protocol that is involved. So right now, ISRO is choosing only this location. We haven't chosen any other location. There should be some problem associated with Kanyakumari, maybe some sort of ionospheric disturbances or maybe proper land area. There could be many factors. But right now, the most probable place is in Tuticorin. Clear? We'll go to the next one. Cynthia. Yes. Coming to the next one. Who was the first Indian in space? I repeat the question. Who was the first Indian to reach the space? So space is basically anything outside the Earth's atmosphere. Who was the first Indian to travel to space? Make random assumptions. Okay, Rakesh Sharma. Any other person? Okay, Rakesh Sharma is quite a household name when we were growing up. Yeah, Rakesh Sharma was the first Indian to travel to the space. Good. Yeah, Jawahar is asking, can we say Kalpana Chawla? Yeah, the main reason why I took this topic is, see, understand, contributions of Indians in field of science and technology, that's there in your main syllabus. So when you talk about the contributions in the field of space science, you can write about Rakesh Sharma, you can write about Ravish Malhotra, but try not to include people who are of Indian origin. For example, if you take Kalpana Chawla, or if you take the recent one, Swati Mohan, who was a part of this Perseverance mission, all these people, they cannot be boasted by saying they are Indians. They are not Indians. They are people of Indian origin. Right now, they are citizens of America. So basically, this is more like a brain drain concept. So don't use it for the points that includes contributions of Indians in the field of space and technology. You can write about Madam Deepankar Banerjee, who is part of this Punch mission. We were talking about the solar mission Punch mission. You can write about Deepankar Banerjee, you can write about Rakesh Sharma, you can write about Ravish Malhotra, or in recent times they have discovered many things about stars. People from Indian Institute of Astrophysics, they have found out many things about low massive stars and everything. So those things you can include, but try to avoid points related to Kalpana Chawla and Sunita Williams. All these people you try to avoid. Good. So first one. Ravish Malhotra is also important because he was training alongside Rakesh Sharma. So both of them were selected together. So this was a joint mission between India and the former Soviet Russia, USSR. So they were planning to travel to a space station called as Salyut, SALUT-7. I repeat, the name is Salyut. Good. So this is similar to the International Space Station. So China had a space station called Tiangong. It's not active. It has been deorbited. And the USSR had space stations called Salyut, that's also deorbited. So right now, ISS, the International Space Station, is the only floating space station right now. That's in low Earth orbit. That's only the present functional space station. No, now we are talking about Salyut 7. So for Salyut 7, Rakesh Sharma and Ravish Malhotra, both of them were training together. So he was the backup astronaut. So if there is something goes wrong with Rakesh Sharma, if he gets unfit or anything, in that case, he was set to replace Rakesh Sharma. Good, that was the plan. So remember, Ravish Malhotra has Kirti Chakra and Rakesh Sharma has Ashoka Chakra. So basically, both of them are the Indians who traveled to space. So first one is Rakesh Sharma. And then Ravish Malhotra. He holds Ashoka Chakra. He holds Kirti Chakra. So they were conferred this award, and they were training to travel to the space station called as Salyut 7. Clear. And next one, we were talking about Kalpana Chawla. So she was part of this space shuttle Columbia STS program that disintegrated in the space in 2003. That came to a sad ending. And Sunita Williams, she is still an active astronaut. She was a US Army pilot. Yes, she is one of the women with most number of time in space. She has spent around 300 plus days in the space. Good. So these two people are of Indian origin. And other Indian's name in space technology was Mr. Rajachari. So he is a part of the astronauts who are training for Artemis mission. I repeat, Artemis mission. It's a manned mission to moon, which is going to be sent by USA. So one person of Indian origin is there in Artemis mission. Clear? Good. So coming to the next one about GRACE FO. So with this, the important missions of India is over. So now we are starting with the global missions, and then we are slowly moving towards astrophysics. Good. The first question, can someone tell me, true or false based question? Good. Let's talk about gravity. So gravity, what is gravity? Basically, it's attractive force between two objects in the universe. Earth is the only, okay, gravity exists only inside solar system. True or false? I will repeat the question. Gravity, the force of gravity exists only inside the solar system. True or false? Try to participate. Okay. Archana says false. Jawar says false. Okay. Okay. So which means gravity is present everywhere. Wherever we go in the universe, the force of gravity is still acting. Good. Gravity exists everywhere. Yes. Second question. The force of gravity between two objects increases when the mass of the object increases. I'll repeat the question. Or in simple terms, bigger the objects, larger is the gravity. True or false? Bigger the object, larger is the force of gravity. True or false? Yes. So object with more mass will have more gravity. Good. So second one, the force of gravity decreases when distance between the two objects increases. I'll repeat the question. The force of gravity between two objects, it will decrease if the force between the two objects, the distance between the two objects increases. So increasing distance, decreasing gravity. True or false? Yeah, it's true. All right. So this is called as Newton's law of gravity. We call it as universal law of gravitation, where it says force between two objects. Repeat, force between two objects is proportional to product of their masses and inversely proportional to square of distance between them. Good, understand? M1 and M2. It will be there in your physics NCERT. I'm just giving a basic introduction. M1, M2. The distance between them is D. So the force of gravity It depends on the mass and it depends on the distance between two objects. Exactly, m1, m2 by d. D square, Cynthia, to be more precise, d square, but yeah, good attempt. So if you want to write it in even more precise way, we have to put it force equals to g. G is universal gravitational constant, m1 into m2 by d square. So this is the universal of gravitation's overall formula. So why I'm saying this now is, we have an interesting mission called as GRACE FO. Good. So GRACE FO, it's a mission by USA. Why I'm saying it's very interesting is, see, the overall idea behind GRACE FO is it's basically going to look at the water movement in different parts of the world. So it's going to analyze how water movement pattern is there, how water is present in underground, on the surface, or in the ice caps and everything. So that's the overall idea of the mission. And how it is implemented is even more brilliant. Good. So basically, GRACE FO has two satellites. So visualize there are two satellites. We have video to play behind, no problem. There are two satellites. So these two satellites, they'll be traveling. They'll be orbiting the world. Good. So whenever the first satellite, when it crosses a rocky mountain surface, good. Let's say this is the surface, and then we have a mountain. Say the first satellite, second satellite, and this is the first satellite. So when the first satellite crosses the mountain area, what will happen? There will be more mass. Mass will be more. So what will happen when the mass is more? Gravity will be more. So because of that, there will be change in the speed of the first satellite. Good. So there will be change in relative motion between the first satellite and second satellite. So based on the minute difference between the movement of first and second satellite, they will be calculating the amount of gravity present at the point. Good. Depending on the amount of gravity, they will be calculating the amount of water presence. So whenever it crosses oceans, the gravity will be different. Whenever it crosses a polar ice cap, the gravity will be different. Whenever it crosses a normal rocky surface, the gravity will be different. So the minute or minuscule changes in the gravity, that will be mapped. So overall, it gives overall gravity map of the world. And based on that, using an algorithm, they are calculating water, how water is present and how water moves across the world. So that's the overall mission's idea. You can write short note about it. I'll play a video. So it's called as Gravity Recovery and Climate Experiment Follow-on. So it's because GRACE was earlier mission. Right now, the follow-on mission is on. It's ongoing now. It's a partnership between NASA and GFZ. Good. We'll go to the next one. The prime idea is to calculate how water is moving around the planet. This gives idea. This is satellite number 1. It's here. And then we have satellite number 2. Both will be traveling separated by some 200 kilometers distance. And it will be constantly firing microwave and laser. So both things will be fired. So depending on the small change in the distance, it will be calculated. So the main reason for GRACE FO mission is this. The ongoing changes in cryosphere. First thing, sea level is rising. And second thing, many people depend on snowpack for their water. The third important thing, change in weather and climate patterns. This is one main reason why GRACE FO is launched. So basically, it tracks fluctuations in Earth's gravity field. This is the overall mission idea. You can write down this point alone. This is for tracking fluctuations in Earth's gravity field. Good. Coming to the next one, this is the overall mission idea. So take a look at this. We have 2 satellites. So when these satellites move, and whenever, so it's constantly tracked. There will be communication between these 2 satellites using microwaves. And whenever it crosses a bulkier place, say when Mars is more, there will be change. The distance between the 2 changes. So there are many other payloads on board. They have a star camera. They have different things. So the complete detail is not needed for us. The only detail that you would need is it sends microwave signals. So microwave signal can be used for tracking distance between 2 objects. They are separated by 200 plus kilometers. Good. When the gravity is stronger, the microwave arranging system will detect it. Good. So the main purpose of this microwave ranging system and mapping the gravity, it provides monthly average gravity field. That's all. Good. So coming to the next one, a similar mission. It's called as ICESat. It's called as ICESat. Again, this is a mission by NASA. This is considered even more important because it's the name itself says it's called as ice satellites. So basically, it checks the change in thickness of the ice caps. Good. It covers the Arctic region, Antarctic region, on the polar mountain caps. So basically, it is checking how the thickness of ice is changing. First thing, it's determining the area, the slope, and thickness. All the 3 factors will be tracked by ICESat. So to check how ICESat works, I'll just play a video. This audio on thingla.
NASA is about to launch the most advanced laser instrument.
Adala matma.
NASA is about to launch the most advanced laser instrument of its kind. The Ice Cloud and Land Elevation Satellite 2, or ICESat-2, will measure changes in glaciers, ice sheets, and sea ice. So to prepare for launch, we're counting down 10 quick facts about ICESat-2. 10,000. That's how many times the ICESat-2 laser will fire each second. More pulses mean more height data. The fast-firing laser will allow us to measure the average annual change in the vast ice sheets down to the width of a pencil. 9 years of data from Operation Icebridge will be added to ICESat-2's new data. The airborne mission bridged the gap between the original ICESat and ICESat-2 with flights over the Arctic and Antarctica. 800 picoseconds, less than 1 billionth of a second. That's the precision at which individual laser photons will be timed as they complete their round-trip journey from the satellite to the Earth and back. 7 kilometers per second is how fast ICESat-2 will zoom above the planet. It'll complete an orbit around Earth in 90 minutes. The orbits will converge around the poles, focusing the data in the regions with the most expected change. 6 laser beams split from 1 on board ICESat-2. That's 6 times the beams of the original ICESat. More beams will cover more ground, or ice, and allow scientists to assess the slope of the surface they're measuring. 532 nanometers, the wavelength of the bright green laser. When these laser photons return to the satellite, filters block any light that's not exactly at this wavelength, keeping the amount of data noise down. 4 times a year, every 91 days, ISAT-2 will measure the same ground tracks, allowing scientists to see how glaciers and other frozen features change with the seasons, including over winter. A 3D look at Earth, now with more height. ISAT-2 will measure elevation to see how much glaciers, sea ice, and ice sheets are rising or falling and give us a more complete picture of our planet. There are two types of ice that ISAT-2 is after, land ice and sea ice. Land ice builds up year after year from snowfall, but sea ice forms when the ocean water freezes. It can last for years or just one winter. Only one instrument, but it's a really good one. The Advanced Topographic Laser Altimeter System, or ATLAS, was built by hundreds of people at NASA's Goddard Space Flight Center to exacting requirements so that scientists, very soon, can measure minute changes in our planet's ice.
All right. So the overall idea is measuring the change in thickness of the ice. Good. So it uses a single laser beam. So understand ISAT-2, and followed by one more thing called as Operation Ice Bridge. You can write about 3. So ISAT-2 is the most recent one. ISAT-1 is over. The mission period is over. So ISAT-2, it is going to combine the data of ISAT-2 along with Operation Ice Bridge. Operation Ice Bridge. So this is again mission by NASA that involves mostly the Boeing and other smaller planes. So that will fly over the ice caps and they will be measuring the thickness of ice. Basically, it uses laser. So if you get a question saying laser can be used for measuring thickness of ice caps, the answer is yes. You don't always use microwaves. You use lasers also. It's a laser instrument to check elevation changes in ice. Coming to ATLAS, there is Advanced Topographic Laser Altimeter System. So that's a system used in ISAT-2. Note these two names alone. Don't write the entire thing, write these two alone. So ISAT used GLAS, that is Geoscience Laser Altimeter System, and ISAT-2 uses ATLAS system. Good. Next one. So we are talking about altimeter systems. So basically measuring the elevation. So India has 2 satellite systems that were measuring the height or the elevation. The first thing was satellite with Argos and Altica, SARAL. So this is comparable with SARAL, satellite with Argos and Altica. And then we had one more mission called as Megatropics. We discussed about these 2 satellites in the last class, SARAL and Megatropics. So SARAL was for checking altimeter changes in ocean, and Megatropics is related to water related studies, hydro studies. Coming to the next one, we are going to talk about Starlink. Can someone tell me what is meant by Starlink? Did you come across a term called as Starlink? Anyone? Starlink. Can someone tell me what is meant by Starlink? Did you come across this term called as Starlink in the news? Frequently repeated from the last year. Okay, so basically it's a satellite-based, SpaceX is building something called as Starlink. So Starlink is basically satellite-based internet service. Good. So instead of having a lengthy junction box and everything, Elon Musk is planning to provide internet using satellites. Good. So right now the satellites that we use for internet connection is generally placed in high Earth orbit. So we were discussing about different altitudes, low Earth orbit, medium Earth orbit, and high Earth orbit. So right now the satellites are placed at high Earth orbit for communication purposes. But in this case, so Elon Musk, the SpaceX company, is planning to place satellites in low Earth orbit, which means less than 500 kilometers above the surface of Earth. Good. So it's going to place more number of satellites. So by the term satellite, constellation of satellites, it's going to be around 12,000 satellites placed in low Earth orbit. Good. So by that, we'll have a network of satellites. So all you have to do is they'll be providing a small type of dish. So it's called a small VSAT antenna. It's a small antenna. So you have to place the small antenna on top of your home, just like you set up your DTH, and then you can connect it directly to your modem through a small device. So it goes on like this. Even in the remote location, say, let's say Northeast or any rural area in your town, they will get a good amount of internet connection that will go up to 100 to 200 Mbps just by using a small antenna. That's the overall idea. Good. So Starlink, it's a program by SpaceX. It will operate at 550 kilometers above the Earth's surface. That is in low Earth orbit. So network of satellites that provide internet. Network of satellites that will provide internet. Can someone tell me any problems associated with this program? What is the main problem associated with Starlink? What is one major criticism that's put on Starlink? Anyone? Any logical assumption? Okay, traffic in low Earth orbit. Good answer. So we'll have crowding of satellites in the low Earth orbit. That's one biggest problem. Yes. Congestion in space. Exactly. So since it's close to 12,000 satellite means the next time we have to launch something else. Let's say we want to launch a satellite to high Earth orbit. So we have to wait for a time where there won't be the Starlink satellites and everything. So it's going to crowd the low Earth orbit. So even if you want to put a satellite in medium Earth orbit or high Earth orbit, you have to check for the avoiding collisions and everything. It's going to be super crowded network of satellites. That's one major criticism put forth on Starlink. Good. So this is artistic impression. Imagine these many satellites, 12,000 satellites. And right now he's planning to expand it to 30,000. He's seeking approval to expand it up to 30,000 satellites around the low Earth orbit. Good. So what are the advantages of this low Earth orbit internet? Can someone say the advantages? Let's talk about advantages. Advantages of satellite-based internet system. Thanks. The disadvantages, congestion, a large amount of space debris will be created. Okay. Immediate connection, high speed. Okay. So the main advantages, it provides high-speed internet because imagine the data you send, it has to travel 35,000 kilometers and it has to return back to the junction box and everything. But imagine if it has to travel just 500 and 500, total of 1,000 kilometers. So which means latency is going to be less. The data latency, it's going to be extremely less, and we'll get high-speed internet connection. That's one main advantage of this. And second thing, it can cover rural areas. It can support important communication systems or any telecast systems in rural areas. So even education can be supported better because we can deliver content using high-speed internet. All the schools in the rural area, all educational institutions, or even the farmers in the rural area, they'll be highly benefited. So the first thing is it's a compactly designed 260 kilogram satellite, and importantly, it uses ion propulsion system, which means it uses krypton gases. Ion propulsion system, it uses krypton gases. I'll tell you shortly what is meant by ion propulsion system. See, instead of using fuel, that is fuel plus oxidizer, or instead of using any electric motor, we are going to use ions. So what is meant by ion? Let's say we have a nucleus, and then we have a lot of electrons around it. If it is balanced, you call it as a neutral atom. That is same number of protons and same number of electrons. That's called as a neutral atom. It holds no net electric charge. So the total charge is going to be 0 because the negative charge by electron is going to be balanced by electric charge by protons. Wherein what is meant by ion? Ion is basically either positive ion or negative ion, which means in an atom, if you bring a charge imbalance by adding an electron, then that's ion. Or if you're going to remove an electron, then that's also a charge imbalance because this will be positively charged, this will be negatively charged. So these are called as ions. The ion propulsion system, basically, it will separate electrons from krypton gas or any other noble gas. Good. So it will have positive ions, and along with it there will be electrons. Good. So there will be cloud of positive ions, and there will be cloud of negative ions, that is electrons. So at some time, whenever power is needed, the satellite will inject this electron into the positive ion cloud. So I repeat, the electrons will be re-injected into the positive ion cloud. So this will create a huge electric discharge, and this force will be converted and used for satellite maneuvering. That's the overall idea. If it wants to make a collision avoidance maneuver, or if it wants to change the track or anything. So basically it will separate the gas, and again it will re-inject the electrons back into the ions. So what will happen? It will create electric discharge, it will create a force, and because of that the satellite can move. The force can be tapped by the satellite for movement. That's the overall idea. So the main advantage is it does not use nuclear fuel, it does not need a fuel and oxidizer. You can reuse it again and again, which means the span of satellite is going to be more economic. That's the overall idea. So we have been generally using argon or neon, but this is the first time krypton is used in ion propulsion system. So all the satellites of Starlink, it uses ion propulsion system. 700 plus satellites are already there in the orbit. I repeat, there are already 700 plus Starlink satellites in the orbit. They use ion propulsion system. Good. So the main advantage of this one is, I'll ask one more question. Is Starlink authorized to operate in India? I'll repeat the question. Is Starlink authorized to operate in India? Do we have Starlink in India right now? Like true or false, yes or no? Any answer? No. So right now Starlink is operational only in United States of America, and it's not operational in any Asian countries. The main reason is Starlink has competitors. Good. So Amazon is planning to launch its own internet providing satellite, and also India also has a satellite system called as OneWeb. So basically it is a combined effort between UK government and Bharti Group. Good. So right now we are not allowing Starlink to operate here. Starlink, it's operating only in United States, and this is the important thing. Phased array antennas. So because of that, a large amount of data can be transferred in a small amount of time with lesser latency, lesser lag basically. Now coming to the competitors, I told you we have, leave this. You could see the most recent launch. You could see how many satellites are stacked. This is basically a payload of 60 satellites. You could see here, 30 satellites on one side, 30 satellites on the other side. So this is just 60 satellites. Imagine 12,000 to 13,000 satellites in low Earth orbit, like a Webb. Good. So similar systems that are planned. The first important one is OneWeb. So OneWeb, we can expect OneWeb internet by the end of next year, by end of 2022 we can expect, because this is jointly held by UK government and Bharti Group from India. They hold equal stakes, 50% plus 50%. OneWeb, Leostar, Canada's Telesat, and Kuiper. Kuiper is important. One more American competitor. So Amazon got approval, Jeff Bezos got approval for their own internet communication system. That's called as Kuiper. Good. All right. From this, we are stepping into astrophysics topic. So astrophysics, for those who are very much interested in astronomy and everything, it will be super interesting topic. And for people who are new to this, it may sound a little boring, but try to understand because we have more questions related to black hole, singularity, about cosmic ray background emissions and everything. So in recent times, you have a lot of questions from astrophysics. So astrophysics is an irrefutable topic. You cannot skip it and go to the exams. Good. I'll give you a basic idea. Before I start with it, can someone tell me what is meant by Big Bang? Not the TV series. We are asking about the normal Big Bang theory. Can someone tell what is Big Bang? Or when did it happen? Why do we talk about Big Bang? Random, 1 or 2 words about what you know about Big Bang. It's fine if you could raise your hands also. I can unmute so that you can tell here. A theory on how universe originated 13 billion years ago. Archana says 13, yeah. 13 billion years ago, how universe originated. So how universe evolved. So event when universe was formed, precisely, yeah. So events that happened when universe was formed, that's called as Big Bang theory. So sometimes we call it as Big Bang explosion, but it's not actually explosion. It was a rapid expansion, we would say. Good. You don't have to write lengthy notes about this Big Bang and everything. So write down whatever we are discussing here. That should be fine. Good. So right now the universe is expanding. Good. So the Big Bang started here. I'll be playing a video for you people after we discuss this topic. So to understand the video better, first you have to observe here. Good. So Big Bang, a theory on how the universe originated. So what is universe? We live in Earth. Earth is a part of solar system. Solar system is a part of the Milky Way, and Milky Way is a galaxy. So like that, we have a lot of galaxies, and all these galaxies collectively we call it as a single thing that's called as universe. So everything that we know and everything that we don't know, collectively it's called as universe. And how this universe formed, where it all started initially. How do we have hydrogen? How do we have helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, a lot of elements, a periodic table full of elements, how it formed. So that's the basic idea about the Big Bang theory. Good. So Big Bang, initially, we believe there was an infinitely small and hot ball of matter. Good. So everything in the universe, it was compressed. Imagine having a small mustard, even much smaller than that, billion times smaller than that. So everything in the universe that is present now, it was an extremely compressed stage. So everywhere you read in NASA or everywhere, it's given as infinitesimally small, extremely hot, and extremely compressed state. That's where the Big Bang started. Good. So all the things were compressed into a small ball of matter in extremely smaller size. So this is before 13.7 billion years. Before we proceed this way, first the question, what was present before this? So we say it started 13.7 billion years ago, everything was compressed, everything is fine. So how did this form? How did this universal small infinite ball of matter form? We have no idea. We have no idea if there was anything that existed before and then it died out and then the Big Bang started. We have no idea right now. So right now, our idea and understanding about universe is much limited. We only start from here. With respect to evolution of universe, we start from the Big Bang. What was there before the Big Bang? It is unknown. To the small brains that we have no idea of what happened. Good. So let's start with Big Bang. First thing. So everything was infinitesimally small, extremely small. Good. So now all of a sudden, it started expanding. Good. So it started expanding, producing a lot of things. The first thing to remember was, understand, we are going to talk what happened in first 3 minutes. I repeat, we are going to talk what happened in first 3 minutes after the Big Bang. We are not going to dwell much deeper like in nanoseconds or everything. When you see the video, it will be there. Don't worry. We are going to talk what happened in first 3 minutes of Big Bang. Why 3 minutes? Because 3 minutes is where nucleosynthesis started. So basically all the nucleus started forming. We have atom. Atom has electrons, and electrons they are orbiting around the nucleus. So the nucleus, it started forming after 3 minutes of the Big Bang. Good. So immediately after the Big Bang, there was no proton, there was no electron, there was no neutron. I repeat once again, there was no proton, there was no neutron, there was no electron, no elements were present. We did not have hydrogen, helium, lithium, beryllium or anything. So basically all we had was quarks. All we had was quarks. So how this quark was formed? So basically leptons fused to form quarks. Hold on. Okay. So initially leptons started forming quarks. So it goes on like this. Imagine it's called as annihilation and separation. So basically leptons, they were smaller particles. These leptons, they fused to form quarks. Again, these quarks annihilate, they split in and they formed leptons again. Again, these leptons fused to form quarks. So this process went on and on and on. If you want to write down, you can write it down simply because we are not going to write any other theory about it. That's where Big Bang started. Good. So leptons to quarks, quarks to leptons, leptons to quarks. So this kept on repeating. Good. At some point, the energy level saturated and all that was left was quarks. There was no annihilation, that is basically there was no destruction and there was no new formation. The universe was left with only quarks. Good. So only quarks were there, leptons were not there. And from quarks, what happened was, again, one more process started. So basically quarks started becoming, or they started combining. So quarks combined in different formats and they formed hadrons. And hadrons, again, they formed neutrons. So from this quark, because of different combination of quarks, imagine quark is not a single type of particle. Quarks are different types of particle. So depending on the number of combinations, we had hadrons, we had neutrons and different type of particles that started forming. Good. So again, quarks to hadrons, hadrons to quarks, it went on. So now we are in hadrons phase. So it's called as hadron era. And what happened was, this neutron, understand, neutron is the main reason for forming protons. I repeat, neutron is the main reason for forming protons. I'll tell you how. What is the charge of neutron? Neutron is I'll ask a simple question. Protons, number 1. Neutrons, number 2. Electrons. For the people observing the class, which is the heaviest or which one has the highest mass? Is it 1 or 2 or 3? Can someone tell me which one has the highest mass? Is it 1 or is it 2 or is it 3? Is it proton or is it neutron or is it electron? Which one has the highest mass? Proton, neutron and electron. Which one has the highest mass? Okay, most of the people answering 2. Good. So which one has the lowest mass or the lightest particle among these 3? Which one has the lowest mass or the lightest particle among these 3? Which one is the lightest particle between these 3? Okay, so most people are answering 3. So understand, the lightest particle is electron and the heaviest particle is neutron. Proton and neutron, they almost have the same mass. Good. So electron is light. Light to which extent? How light it is? So imagine the rest mass of one proton. I repeat, the rest mass of one proton will be equal to 1836 electrons. So electrons have extremely, almost negligible mass. So if you keep a balance, you can keep proton on one side, and then to balance this mass, to keep it in a balanced way, you have to keep 1836 electrons on the other side, which means electrons are extremely small, extremely light, almost has negligible mass. Good. So what happens is, if you arrange it in an increasing order of mass, it goes on like this. If you arrange in increasing order of mass, it's electron. So electrons are having less mass. Compared to it, proton has more mass. Compared to proton, neutron has highest mass. Good. So this is negatively charged, this is positively charged, this is neutrally charged. it has no charge. The net charge is 0. Good. So initially when the Big Bang was happening, when we had quarks and hadrons, understand, basically neutrons formed protons and electrons. So basically neutral charge, it split into two charges called as proton and electron, very important one. So basically one neutron by beta decay to split into a proton and electron. So this is where the nucleosynthesis starts. This is where nucleus forms. What forms the nucleus? Yeah, rest mass is basically when the particle is not moving, when there is no relativistic variation in the velocity. So imagine you keep an electron in a standard state without movement. That's called as rest mass. It's a technical term. Remember it as mass of electron. That's enough. Rest mass means without movement if you place it in a stationary position. Good. Okay. So neutrons, they started splitting up into proton and electron. Good. So this is even in textbook it's called as beta decay. We call it as beta decay, one form of radioactive decay in which a neutron will split up into proton and electron. Good. So initially, leptons forms quarks. Quarks splits up into leptons. Leptons annihilate to form quarks. This process was repeating, and then only quarks was left over. So the quarks started forming hadrons and then neutrons, and then neutrons started forming protons, electrons. So now we have protons, now we have electrons, now we have neutrons in the universe. We have not even passed 3 minutes of the Big Bang. I repeat, all these happenings. It's in few seconds, like 200 plus seconds. That's all. So we are yet to cross the 3rd minute of Big Bang. Good. So we are yet to cross the third minute of the Big Bang. And now what happens is protons and neutrons, they start combining to form nucleus. All unstable nucleus. Electrons they were not captured into the orbit. Right now we have a nucleus, different nucleus of hydrogen and everything. So neutrons and protons, they basically combine to form nucleus. So this is called as nucleosynthesis era. This happens here. In 3rd minute, you can roughly write it's called as nucleosynthesis era. Good. So in 3rd minute, nucleus were formed. And even now, the elements have not formed. So what causes to form an element? The electrons, it has to be trapped around the nucleus. So basically, the electrons should start orbiting the nucleus, and that's where elements will be formed. So right now, we have only nucleus. We don't have anything else. Good. So this is with respect to 3 minutes from the Big Bang. And after 3 minutes, we are directly skipping to 390,000 years. Sorry, 380,000 years. So after 380,000 years, elements started forming. Good. Elements means basically, importantly, hydrogen and helium. Hydrogen and helium started forming. And from hydrogen and helium, they started combining to form lithium, beryllium, boron, carbon, nitrogen, oxygen, neon, on and on and on and on. So the nuclear fusion process went on happening in stars, and then it started forming other elements. Good. From 3rd minute, we have directly skipped to 380,000 or 380,000 years because this much data is sufficient. Because the questions that were asked with respect to Big Bang, basically it's to test our basic knowledge, basic understanding, because we are not going to write an exam to get into the Indian Institute of Astrophysics or anything. So this is basically we are aspiring civil servants. So don't worry. They'll ask only the basics about Big Bang. This much is sufficient. Good. So after this, I'll just play a video. You can watch it. And if you have any doubt about it, you can raise the questions after the video. I put video with subtitles for better understanding.
The beginning of everything, the Big Bang. The idea that the universe was suddenly born and is not infinite. Up to the middle of the 20th century, most scientists thought of the universe as infinite and ageless. Until Einstein's theory of relativity gave us a better understanding of gravity, and Edwin Hubble discovered that galaxies idea that the universe was suddenly born and is not infinite. Up to the middle of the 20th century, most scientists thought of the universe as infinite and ageless. Until Einstein's theory of relativity gave us a better understanding of gravity, and Edwin Hubble discovered that galaxies are moving apart from one another in a way that fits previous predictions. In 1964, by accident, cosmic background radiation was discovered, a relic of the early universe, which together with other observational evidence made the Big Bang the accepted theory in science. Since then, improved technology like the Hubble telescope has given us a pretty good picture of the Big Bang and the structure of the cosmos. Recent observations even seem to suggest that the expansion of the universe is accelerating. But how did this Big Bang work? How can something come from nothing? Let's explore what we know. We can ignore the beginning part for now. First of all, the Big Bang was not an explosion. It was all space, stretching everywhere, all at once. The universe started very, very, very small and quickly expanded to the size of a football. The universe didn't expand into anything, space was just expanding into itself. The universe cannot expand into anything because the universe has no borders. There is, by definition, no outside the universe. The universe is all there is. In this hot, dense environment, energy manifested itself in particles that existed only for the tiniest glimpses of time. From gluons, pairs of quarks were created, which destroyed one another, perhaps after giving off more gluons. These found other short-lived quarks to interact with, forming new quark pairs and gluons again. Matter and energy were not just theoretically equivalent, it was so hot they were practically the same stuff. Somewhere around this time, matter won over antimatter. Today, we're left with almost all matter and nearly no antimatter at all. Somehow, 1,000,000,001 matter particles were formed for every 1,000,000,000 particles of antimatter. Instead of one massive ultimate force in the universe, there were now several refined versions of it acting under different rules. By now, the universe has stretched to 1 billion kilometers in diameter, which leads to a decrease in temperature. The cycle of quarks being born and converted back to energy suddenly stops. From now on, we work with what we have. Quarks begin forming new particles, hadrons, like protons and neutrons. There are many, many combinations of quarks that can form all sorts of hadrons, but only very few are reasonably stable for any length of time. Please take a moment to appreciate that by now, only 1 second has passed since the beginning of everything. The universe, which has grown to 100 billion kilometers, is now cold enough to allow most of the neutrons to decay into protons and form the first atom, hydrogen. Imagine the universe at this point as an extremely hot soup, 10 billion degrees Celsius, filled with countless particles and energy. Over the next few minutes, things cooled and settled down very fast. Atoms formed out of hadrons and electrons, making for a stable and electrically neutral environment. Some call this period the Dark Age because there were no stars and the hydrogen gas didn't allow visible light to move around. But what's the meaning of visible light anyway, when there's nothing alive yet that could have eyes? When the hydrogen gas clumped together after millions of years and gravity put it under great pressure, stars and galaxies began to form. Their radiation dissolved the stable hydrogen gas into a plasma that still permeates the universe today and allows visible light to pass. Finally, there was light. Okay, but what about the part we didn't talk about? What happened right at the beginning? This part can be defined as the Big Bang. We don't know at all what happened here. At this point, our tools break down. Natural laws stop making sense. Time itself becomes wibbly-wobbly. To understand what happened here, we need a theory that unifies Einstein's relativity and quantum mechanics, something countless scientists are working on right now. But this leaves us with lots of unanswered questions. Were there universes before our own? Is this the first and only universe? What started the Big Bang? Or did it just occur naturally based on laws we don't understand yet? We don't know, and maybe we never will. But what we do know is that the universe as we know it started here and gave birth to particles, galaxies, stars, the Earth, and you. Since we ourselves are made of dead stars, we are not separate from the universe. We are part of it. You could even say that we are the universe's way of experiencing itself. So let's keep on experiencing it until there are no more questions to ask.
Screen sharing off, Nilna. So that's the overall idea. This is to give you a basic introduction. So I think we made a small error there when everything started. Basically, gluons were annihilating to form quarks. It was not leptons, it was gluons. I repeat, you can make a small change. So immediately after the Big Bang, gluons combined to form quarks. Gluons annihilated to form quarks, and then quarks split up into gluons. So gluons and quark circle was going on, and then it stopped. And after the gluons and quark circle stopped, so quarks started forming leptons, hadrons, and everything. Is it clear? Please make that correction. I repeat once again. Quarks were basically formed from gluons, not leptons. Corrected. Good. And now coming to the next part, what are the problems or what are the main studies or mysteries related to the Big Bang? So first thing, after Big Bang happened, once the Big Bang happened, it emitted a lot of radiation. Good. So those are called as cosmic background radiation. It's called as CMB, cosmic background radiation. This cosmic background radiation is providing us more data about the Big Bang. This is the overall idea. Good. And now the most mysterious thing is the universe is expanding. Good. I repeat, the universe is still expanding. Even after 13.7 billion years, the universe has not stopped expanding. It's still going on. It's still expanding, going on and on. And the recent discovery is actually the expansion of universe is accelerating. I repeat, the expansion of universe is accelerating, which means universe is expanding even more faster than it used to be. Good. So this brings a lot of questions. First, a basic question I'll ask you. Imagine this is Sun, and then we have Mercury, and then we have Pluto here. Which one will be traveling faster? Is it Mercury or is it Pluto? I'll repeat. Is it Mercury or is it the Pluto? Which one will be traveling faster? Yeah, Mercury should be traveling faster because it gets more gravity from Sun compared to Pluto. Good. Mercury will be traveling faster because it's much closer to Sun. So it can have more gravity and it can travel faster, which means this is traveling faster, this is traveling slower. But now, on a large scale, that is even more large scale, if you take a galaxy, good, let's say we take a galaxy, and we have a star at two different locations. Let's say we have a star here, and then we have a star somewhere in the outermost region. Good. So we have a star here, and then we have a star in the outermost region. The entire galaxy is spinning. If you see, this star and this star, they'll be spinning at the same rate. They'll be having the same speed. They'll have same rotation speed. So the main question here is, there is more space between this star and this star. Then in this case, How is this spinning faster? This is supposed to spin slower, because if you take Mercury and Pluto, Mercury is spinning slower compared to it, Pluto is traveling faster. So similarly, if you go on a larger scale, compare it to an entire galaxy scale, so the stars that are found at the outermost part of the galaxy, they should be slower. Technically, this should be slower. And the stars that are found in center of the galaxy with massive black holes and everything, this is supposed to be faster. But if you see, they will have uniform velocity. So what is this? What brings this uniform velocity? So what is present in the space? So this main question is answered by Einstein's theory of relativity. Good. So Einstein said a simple statement: vacuum is not empty. I repeat, vacuum is not basically empty space. It is filled with something that we don't know. That is the overall idea. I'll repeat once again. What does mean by a vacuum? We call it as something that's totally empty. No, vacuum is not empty. Vacuum is not an empty space. There is something filled in the vacuum. There is something filled in the outer space that we don't know. We call them as dark energy and dark matter. Good. Can someone tell me how much dark energy or dark matter together is present in the universe in terms of percentage? Make a random guess. What is the amount of dark energy and dark matter present in the universe? We determine it only using gravity. It does not emit light. It does not have a mass, nothing. So only gravity is the sole factor for studying the dark matter and dark energy. Can someone make a random assumption to how much percentage of the total universe do we have dark energy and dark matter? 80 to 90%, exactly. So it's close to 96%. I repeat, all the galaxy which we see, all the stars which we see, and all the elements and everything, they constitute only to 4% of the universe. So we know only 4% of the universe. Rest of the thing, it is all unknown. It's called as dark energy and dark matter. Good. So it's expanding. And Hubble's law says galaxies are moving away at a greater speed, which means there is accelerated expansion. So the main question that we have now is, what is accelerating this expansion? Why is that when stars get far away, they accelerate, they expand even more faster? So the main reason is, right now we believe it is filled with dark matter and dark energy. Good. So initially Big Bang, so the galaxies were drifting away slower, and right now it's drifting faster. There is accelerated expansion. The key word is accelerated expansion, and the main reason is dark matter and dark energy. Okay, note on this roughly. All the atoms that we know is only 4%. All the things that we see in terms of matter and radiation, it's just 4% of the total universe. Other things are dark energy and dark matter. If you want to write definition for dark energy and dark matter, you can say dark energy and dark matter are properties of space that is unknown to human. That's all. Dark energy and dark matter are the properties of space that are unknown to human. Basically, something is filling the space. We don't know what is the type of particle present inside. We don't know what are the radiations present inside. All we know is there is something that's accelerating the expansion of universe. There is something that is filling the space between the galaxies. That's why the galaxies are expanding faster. They are spinning at equal rates. We know it's because of dark energy and dark matter, but we don't know the constituents of dark energy and dark matter. This is the overall idea. Good. So what is the difference between matter and energy? That's one basic definition you should understand. First thing, see matter. Matter, it is basically anything that occupies space. Anything that has mass and volume. So anything that occupies a volume and anything that has mass, you call it as matter. For example, all the things, everything that you use, we ourselves, chairs, cars, everything, it's matter because it has a particular mass, it's a particle, and it has certain amount of volume. Good. Coming to radiation. So matter and radiation. So radiation means basically it has the ability to do work. Or even more precisely, energy with ability to do work. Radiation is energy with ability to do work. So all the electromagnetic waves, which that includes radio, microwave, infrared, visible light, UV rays, X-rays, gamma rays, alpha, beta, everything it's form of radiation. There are no particles inside. We know X-rays and everything. It has no elementary particles like protons, neutrons, and electrons, but they have a lot of energy. So basically, they are energy with ability to do some work. We use it for communication. We use it for medical purpose. So radiation, it is energy with ability to do work. And matter, it is anything that is more like a particle. It occupies a mass and a volume. Good. So we have dark energy and dark matter. We don't know what is present inside. Totally unknown. And after this, we have to start with Hubble's law. Yeah. So I'll be sending these pictures and notes to your Telegram channel. Anyway, you can write short notes. So galaxies are moving away at a speed proportional to their distance. Greater the distance, faster is the drifting speed. That's because dark energy and dark matter is more. UPSC had asked questions about dark energy and dark matter, about black hole, about singularity, about cosmic ray background. I put old question papers at the end of this class. There are a few slides with the old question papers. We'll solve it, no problem. You write it down now. Done. So I think we'll take a break, refresh yourself. I understand it's a nice Sunday noon, but then we are starting, talking about the Big Bang, stars, and everything. So it might be a little sleepy. You take a good break and come back, because the next topic is much important. We are going to talk about life cycle of stars. So basically, how stars are formed, how stars die, and what are the different classifications of stars. So this is very much important, because in the last 2 years we have more data and more current affairs related to stars and black holes. Good. So take a break and come back in 10 minutes maximum. Good. If you have any doubts till that, you can drop a message here. I'll be answering you people. Shall we start? Hope everyone are back online. To the person who asked about the gluons and quarks part, I sent you a lengthy message. Did you read it? Is it clear? SIA AD 2050511. I can't see your name. Is it clear? Yeah, okay. Now coming to the stars. Question number 1. Let's go on a true or false model. Good. So Sun is a supermassive star, or Sun is classified as supermassive star. True or false? I'll repeat the question. Sun is classified as a supermassive star. True or false? Cryosphere means anything that is covered by sub-zero temperature, basically ice caps. We call it as cryosphere. Hydrosphere is basically filled with water. Cryosphere is filled with the materials that has less than 0 degree. When what happens at 0 degree? Basically ice is formed. So all the sub-zero degree temperatures, that includes all the Arctic, Antarctic or Himalayan ice caps, where the temperature drops below 0, you call that region as hydrosphere. Atmosphere with water, hydrosphere with hydrosphere with water, atmosphere with air. Cryosphere, it's basically filled with ice. Is it clear? Akash, clear? Regions filled with ice, shortly. Okay. Yes. So mostly the answer is between true and false. The answer is false. Good. So our sun is not a supermassive star on a universal scale. For solar system scale, the sun is massive. I understand, because basically you can accommodate somewhere close to 13 billion Earth inside the sun. Imagine 13 lakh Earth inside the sun can be accommodated. So it appears massive and humongous to us, but the actual thing is, on the universal scale, Sun is classified as yellow dwarf star. Yellow dwarf, a much small sized star. Good. So there are supermassive stars that are a million times or billion times larger than Sun. So we are going to talk how star is formed. So for today's class, so we'll be talking about the formation of stars and then how black holes are formed. So we'll finish the class with that, because I don't want to push the class much lengthier. All you have to do is, when you come to the next class, you have to read about Big Bang once again, you have to read about life cycle of stars, you have to read about the black holes again. So that based on the basic understanding, good, once your foundation is strong, then we can go to the current affairs part. So today is more like static part. So we'll start with life cycle of star. You can write notes for this, but we are going to explain the entire thing on how star is formed. So the first thing, you can write it in this way. In a landscape form, then I'll be explaining the individual parts. So first thing is from nebula. Nebula to protostar. Protostar to I cannot draw the entire flow chart here, because the board is lesser. So you people don't fill your page. So this is like, put it in landscape mode. Try to write it this way. We have more things to go on the right side. Either write it horizontally or you can write it vertically. It depends on your convenience. I'm just going to write down the sequence on how stars are formed and how they die out. Starts at nebula, then protostar, and then main sequence star. They write it in a landscape mode like this, or take it like this and then start splitting up notes, so that you can revise it easily before going to the exams. Nebula, nebula to protostar, protostar to main sequence star. Good. After main sequence star, we have red giant star. The next phase is red giant. Clear? So from red giant, we are going to split the flow chart into two. Good. I'm going to erase this. I'm going to continue from there. You can continue in your notes from here. Whatever we are writing, you continue from the red giant phase. So red giant phase, till the red giant phase, it's common for all the stars. And from red giant, we are going to classify the stars into two types: supermassive stars and low mass stars. First is low mass stars. Next is supermassive stars. Good. So depending on their mass, we are splitting it into two. So low mass star, it becomes planetary nebula. And planetary nebula, it becomes white dwarf. I'll explain the individual components. Don't worry, you write it down now. From white dwarf, it becomes black dwarf. Good. So coming to the supermassive stars, they form, next one is supernova explosion. Good. After supernova explosion, again there are two classifications. First one is, it can either become a neutron star or it may form a black hole. So supermassive stars, they undergo something called a supernova explosion, and then they may become neutron star or they may become black hole. Good, clear. We'll go to the next one. Can I erase this? Okay. A basic explanation of the topics, the process. First one will start with nebula, on how it becomes nebula to protostar. So nebula is basically a cosmic space where different elements are present, including hydrogen and everything. Good. So because of gravity, hydrogen will be attracted. So I repeat, two hydrogen will be attracted because of gravity in stellar nebula. So in nebula, what will happen is hydrogen attracted. So once they are attracted, they start spinning. So once they start spinning, there will be increased kinetic energy. And because of increased kinetic energy, heat will be produced. And this stage is called as protostar. So the region or a state before actual star formation, if you'll be reading in history as proto-Shiva in Indus Valley civilization. So like that, it's called as protostar. So before the star is formed, before the star attains a proper physical form, this stage is called as protostar, basically having high temperature and high kinetic energy because of spinning of hydrogen. Clear? Can we go to the next one? So right now we are protostar. The next stage is from protostar to main sequence star. So what happens in nuclear fusion generally? Do elements join or do elements split? I repeat the question. What happens during a nuclear fusion? Generally for hydrogen, what will happen in nuclear fusion? Yeah, generally lighter nuclei fuse to form heavier nuclei. That's what happens. So right now, protostar is having a lot of hydrogen atoms. So what will happen is these hydrogen, they will combine, they will fuse to form helium. Good. So hydrogen fuses. Hydrogen fuses. So because of the hydrogen starts fusing, so the star will be compressed because basically more elements forms smaller elements. So size is compressed, and once size is compressed, it starts glowing. Comparatively stable state, this is called as a main sequence star. Basically, the hydrogen will fuse, the size will be compressed, and it becomes stable, and the star starts glowing. So we call this stage as, you lost connection once again, nebula stage. So nebula stage is basically a space between the galaxies in the intergalactic space where a lot of elements are present. So starting from hydrogen and different elements that were previously seeded by the dead stars. So all these elements are present. And hydrogen, two hydrogen is attracted because of gravity, and then because of the attraction, they start spinning on a common axis. So because of the spin, what will happen is there will be more kinetic energy. So more kinetic energy means more thermal energy. Heat will be produced, and then it starts glowing. So that's what we call as protostar. Is it clear? The person who lost the connection. So that's what we call as protostar. And after protostar, we're discussing about main sequence star. So these hydrogen fuses. So basically, hydrogen fuses to form helium. Yes. Coming to the next one, how main sequence star becomes a red giant. Next one. Main sequence to red giant. So before we write this, write down this thing called as hydrostatic equilibrium. This is very much important. We call it as hydrostatic equilibrium. So what is the shape of Earth? It's almost spherical. We call it as geoid shape. What is the shape of Mercury? What is the shape of Venus and everything? Almost all the planets are spherical in shape. Good. So it's called as hydrostatic equilibrium. Hydrostatic equilibrium means it is delicate balance between gravity and radiation. I repeat, hydrostatic equilibrium means basically it's a delicate balance between gravity and radiation. So imagine this is Earth. So what happens inside Earth? Inside the Nephi layer, there is radioactivity, and because of that, material is constantly coming to upper part of the Earth. So you have read in geography, generally asthenosphere, it is semi-solid in nature. It is highly fluidic. So generally, elements from the interior of the Earth, it is constantly coming to asthenosphere, and sometimes because of volcanic activity, it is coming outside. So basically, elements from interior of the Earth through convection, it is coming up. So that's why the major Earth plates are moving. You would have read. So which means Earth is giving out energy from inner side to the outer side. So towards the outer side, towards the surface, the Earth is constantly pushing radiation. So radiation is high in Earth. So at the same time, what is meant by gravity? Basically the force of attraction. So Earth has greater mass, which means it has greater gravity or incoming gravitational force. So gravity is the force that is acting towards the inner side. So gravity is also high. So this balance between radiation and gravity is very much important for a planet to have a rigid shape. I repeat, the balance between radiation, that is energy flowing to the outer side, and the gravity, energy flowing towards inner side. So there should be balance between radiation and gravity so that an object will remain in a standard geometric form. So this is called as hydrostatic equilibrium. So Earth has hydrostatic equilibrium, Sun has hydrostatic equilibrium. All the planets in the solar system, they have hydrostatic equilibrium. Similarly, the stars will also have hydrostatic equilibrium. Clear? Star has hydrostatic equilibrium. So now what happens is, in main sequence star, so in main sequence star, there will be a lot of hydrogen inside. So these hydrogen, they'll fuse to form helium. So I repeat, 4 hydrogen, they'll fuse to form helium-24 plus positron plus neutrino. This is the standard equation for almost all the stars. So basically the hydrogen, it will fuse to form helium, which means inside the star, hydrogen is fusing and it is forming helium. So step number 1, hydrogen fuses to form helium. So which means there is radiation and there is gravity, which is perfectly balanced in main sequence star. So now what will happen is, at some point, the hydrogen will run out of energy. So there will be more helium present inside and there won't be hydrogen present inside. So what will happen? The fusion will cease. It will stop. So at this point, gravity will increase, radiation will reduce. So what will happen? The star will collapse on its own gravity. See, listen again. Hydrogen is fusing to form helium. It's a repeated process. It's an ongoing process in main sequence star. So once all the hydrogen runs out, once there is no more energy for hydrogen to fuse and form helium, what will happen? There will be very lesser hydrogen and there will be more helium. So at this point, the radiation ceases. The radiation stops. So because of that, the gravity overtakes radiation. So gravity will compress the star and the star will implode. It's not explosion, it's basically implosion, because the star collapses on its own gravity. So no more hydrogen to fuse. Star implodes. The star will implode and it will form something called as red giant star. Repeat, it's called as red giant star. What will happen means, the core of the star reduces in size. There will be a smaller core and the outer part, it will cool down. So the cooled part will appear red in color. So that's why it's called as red giant star. So repeat, there will be a core and the outer part will be much cooler. Because of the compression, the outer part will be cooled down. So the cooled down part is red in color. So understand, red hot we call, but actually white flame is having more energy compared to blue and red. So red is comparatively less hotter. If you take a look at any flame or any star, the star that's white in color, it has more temperature. And next is the blue and next is the red. So red is basically, even if you look at your gas stoves, whenever there is improper combustion, when there is some dust inside, it will form an orangish flame. So basically red is having lesser temperature in flames. So when the star cools down, the outer part is red in color. So basically red giant phase is comparatively cooler phase. Is it clear? Any doubt till this? Red giant phase. What is neutrino? Neutrino is a subatomic particle. Similar to proton, neutron, electron. It does not contribute to mass number or atomic number. It's a subatomic particle. So similar to hadrons and leptons, this is a subatomic particle that does not contribute to mass number or atomic number. Good. So right now we are in red giant phase. So from red giant phase, we have two classification, that is two path followed by the stars depending on their mass. So first is low mass star. So what is low mass star means? Up to 10 times the solar mass. So all through the astrophysics, if I'm writing m followed by a subscript 0, it means solar mass, mass of the sun. I'm going to use m0. So it is basically solar mass, mass of the sun. So the stars which has mass up to 10 times the mass of sun, we call it as low mass stars. Good. And then coming to the next one, we call as supermassive stars. stars with greater than 10 times the solar mass. Those are called as supermassive stars. First, we are going to read about low mass stars. First, we are going to explain from red giant phase what happens to a low mass star. Clear? First one. Low mass star. It's in a red giant phase now where the core is having a lot of helium and the outer part is cooled down. So once the star implodes, once it reduces or compresses in size, what will happen is there will be increased energy. So imagine you have 100 molecules in a larger can and then you compress the 100 molecules in a much smaller can. What will happen? There will be increased thermal energy, which means there is more heat present for the helium to fuse now. Because initially when it was a main sequence star, hydrogen was fusing to form helium. And right now the star has imploded. So the core of the star has more temperature now, which means helium can further fuse to form other elements. If you look at the periodic table, what is there in the periodic table after hydrogen and helium? Next we have lithium, beryllium, boron, carbon, nitrogen, oxygen. It goes on and on. So what will happen is these helium, it will start fusing. It will start fusing to form other elements. So it goes on. Helium fuses to form heavier elements. Fuses to form other elements, you can write simply. Then also this process, again now there is hydrostatic equilibrium because helium is giving out radiation and there is gravity. So there is a delicate balance between radiation and gravity. Good. This goes on and there should be somewhere where it stops. Yes, it stops when carbon is formed at the core. So in the helium, it fuses to form multiple elements and it goes on till carbon. So once carbon is formed in the core of the low mass star, there is no more energy to fuse. So what will happen is, again, the gravity will increase, the radiation will reduce or cease, and then there will be one more implosion. Star collapses under its own gravity. So the star will collapse under its own gravity. Again, the size of the star reduces. And then this process of implosion, it is called as, this process, collapsing under its own gravity, is called as planetary nebula. Repeat. This implosion is called as planetary nebula. The stage where carbon is formed at core of the star and then the star collapses under its own gravity, you call it as planetary nebula. So then what will be left in the core? Once there is planetary nebula, the star collapses. We call the implosion process as planetary nebula. Okay. So what will be left out after this implosion means there will be a small amount of extremely compressed star that is present. Good. That compressed star is called as white dwarf. White dwarf. It's extremely compressed. It's extremely compressed and it's hot. The temperature is high. Good. So what will happen is now the white dwarf will start cooling down. The white dwarf will start cooling down, and then once it's cooled down, once it runs out of energy, it will form something called as black dwarf. White dwarfs, it cools down to form black dwarf. Clear. So what happens after the black dwarf is unknown. We believe it may explode and then seed everything into the planetary nebula. That's what we believe in, because the entire universe, it does not have a black dwarf till now. There is no black dwarf. We only have stars up to white dwarf, and it will take another billion years at least for the white dwarf to cool down. So the oldest known white dwarf, for your basic understanding, the oldest known white dwarf So it has lost only 0.2% of its energy. Just 0.2% of the energy has run out, which means another 99.8% of the energy has to cool down before it forms a complete black dwarf. So the entire mankind, we may not be present to look what a black dwarf looks like. So right now we have only white dwarf stars. Based on a theoretical understanding, we think once it runs out of fuel, it will form a black dwarf. So understand, there are no black dwarfs in the universe. Why I am repeatedly saying is, there was a newspaper article saying when we will get to see black dwarf. There was an explanation in Forbes magazine, and the conclusion was humans won't be present probably to look at a black dwarf, because the oldest known white dwarf, it's still active and running, has lost only a fraction of its energy. Good. Now coming to massive stars or supermassive stars. From red giant phase, the supermassive stars. Before we start this, I'll ask a general question. Which nucleus is the most stable nucleus? Of the entire elements in the periodic table, which element has the most stable nucleus? Stable in the terms, we have to spend a lot of energy to break it. We cannot break the nucleus of that element. We need immense energy to break that element's nucleus. Any idea? Which is the strongest or the most stable element known to mankind? Of the entire ones in the periodic table, make random attempts, whatever that comes in your mind. The strongest element or the most stable element. Okay, maybe carbon. Good. Any other answer? This is there in your physics book, core physics. I will give a basic introduction. Which is considered to be more stable? So the answer is iron. Good. The answer is iron. So we calculate something called as binding energy. I repeat, we calculate something called as binding energy. So basically the energy spent to form a nucleus, it's called as binding energy. So if you plot a graph with mass number on the x-axis and binding energy per nucleon on the y-axis, but starting from 1, that is basically what has a mass number 1, that is hydrogen has a mass number 1. So it goes on. The binding energy will spike, it will increase, and then it will decrease. This is for the entire periodic table, starting from mass number 1 till number 200 plus. Good. So the graph will reach its peak at iron. Fe5626 has the highest binding energy. You have to spend around 8.8 mega electron volt of energy to split the iron atom. Good. We don't need a core physics, but this is just for basic understanding. Iron is more stable. It is difficult to break iron, or it is difficult to fuse elements after iron. So iron is extremely stable. Good. Now, what happens in red giant star, after the red giant phase in a supermassive star? So this has more energy, this has more kinetic energy and more thermal energy. What will happen is hydrogen, here, hydrogen will fuse to form helium. Okay. Helium will fuse to form many elements. It goes on. It doesn't stop at carbon. In low massive star, helium fused to form carbon and it cannot undergo further fusion. But in this case, it goes on and on and on and forms iron. Till iron, all the elements are formed inside supermassive stars. This is highly significant because, understand, all the elements that we know till iron, they are formed in stars only. Hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, neon. All the elements till the first 26 elements in the periodic table, they are formed inside supermassive stars. They were formed inside supermassive stars, and after an explosion, it was spread throughout the universe. So all the elements which we are using, including the lithium in the batteries and everything, once upon a time it was there somewhere formed inside a star. Good. So helium fuses and goes on till it forms iron. Once it forms iron, the star cannot take it anymore. It cannot fuse iron. It cannot form any other elements because it needs more energy. What will happen is, again, the radiation ceases, gravity increases. After iron is formed, star collapses under its own gravity. this gravitational collapse. It's called as supernova explosion. Wait, you write it till this. I will give additional step. So after iron, star collapses under its own gravity. We'll stop here. I'll explain further. Clear? So now star has collapsed under its own gravity. All the iron is compressed into a smaller region. So what will happen here is a pictorial representation for your understanding. You have a lot of iron. And then the star collapses under its own gravity, pushing iron nuclei to a smaller space. So what will happen when you compress it to a smaller space? There will be increased thermal energy and iron will repel each other, and now there will be an explosion. I repeat, now there will be explosion. For the first time, we are using the term explosion. Till now, we have been using only implosion, basically star collapsing under its own gravity. What will happen now is iron will be compressed and kept in a smaller state. There will be increased thermal energy, and iron molecules, basically the nuclei will repel each other, and now there will be an explosion. So by this explosion, iron will be seeded to the outer part of the star. Pay attention to the arrow given in the opposite direction, which means this is basically explosion. So this explosion is called as supernova explosion. In that case, planetary nebula was an implosion. In this case, supernova explosion means basically explosion. Things being expelled outside. Clear? So in supernova stage, the star will explode. Elements will be seeded into the universe. And now there will be increased thermal energy. Now what will happen is, the iron will fuse to form heavier elements. The iron has higher energy now. More thermal energy is provided to iron. And because of that, all the higher elements like all the uranium, strontium, everything, it was formed after supernova explosion. Basically, it's formed from iron. All the heavier elements, strontium, californium, you take uranium, thorium, plutonium, every heavy element, it were formed after supernova explosion. Iron started fusing to form heavier elements. Clear? So, okay, the star has exploded. Not the entire star will explode. There will be some remnants after the explosion. So after the explosion, supernova explosion takes place, there will be leftover elements, or there will be leftover star. So depending on the remnant mass, depending on the leftover mass, post supernova explosion, what is left over in the star, depending on it, we classify it into two types. One is neutron star. The other one is black hole. One of these two things will be formed depending on the mass. Depending on the mass, one of these things will be formed. So when will neutron star form means, see, if the leftover or remnant or leftover mass of the star is around 1.4 times the solar mass, up to 3 times the solar mass. Solar mass is mass of the sun, I told you. So if it is somewhere between 1.4 times the mass of sun up to 3 times the mass of sun, it will form neutron star. If the leftover mass or the remnant mass is greater than 3 times the mass of sun, generally black hole is formed. So this is how the black holes which was there in news in 2019 for being photographed. This is how black holes are formed. Clear? We'll go to the next one. Any doubt in this? Take a look at this picture. They're given two paths. So first one is from star forming nebula. Protostars are formed. This is for low massive star. And then sun-like stars, basically star that has lesser mass. And then it forms red giant. So what happens in red giant? Hydrogen, helium fuses to form carbon, and then there is planetary nebula. So after planetary nebula, what is left over? White dwarf is left over. So and after that, black dwarf will be formed. It's not given here. Coming to massive star on the other side, protostar followed by massive star, that is main sequence star. Then we have red supergiant, and then there is supernova explosion, last one which we discussed. And after supernova explosion, two possibilities are there. Either it will form neutron star or it will form black hole. If the remnant mass is more, it forms black hole. If the remnant mass is less, it forms a neutron star. Take a look at this picture and let me know if you have any doubts. If people have any doubt, please drop a message. I'm watching the chat. Yes, at end of the cycle, everything will be back to nebula. At end of the star, at some point when everything finishes, all the elements will be seeded into nebula again. Again, one more star will start forming. Sun-like star, okay. So sun is in dwarf stage. It will not reach white dwarf stage in any near time because you can write down the statement. Smaller the mass of star, greater is the lifetime. I'll repeat the statement. Smaller is the mass of a star, greater is its lifetime, because it won't fuse more atoms, more elements inside. For example, the sun, it has hydrogen and helium. So once it forms helium, what happens? If you remember the first class, we were talking about different regions in the sun. It has a core, and then we have radiative zone, and then we have convective zone. So convective zone basically sends hydrogen, helium, and plasma, everything to the surface of the star, which means sun will not collapse under its own gravity anytime soon, because sun is not forming uranium, sun is not forming carbon, sun is not forming anything. It's purely plasma. Since it's an average star, it won't collapse under its own gravity anytime soon. So sun is in a stable form. It is right now in yellow dwarf stage. The sun will not run out of fuel. It won't collapse under its own gravity. It won't form heavier elements in its core. Clear? So the larger the star, lesser is the lifetime. If the star is larger, all the reactions will be accelerated. It will form carbon, iron, and everything. It will undergo explosion, and then it will form a black hole or a neutron star. Is it clear, Akash? All these are specific colors. Yeah, we named it depending on our observation. If it's emitting a red, yellow, we have yellow dwarf, we have orange dwarf, we have brown dwarf stars. So depending on the light they emit, depending on the polarimetric techniques, depending on the color we observe, we generally name it this way. Different dwarfs. Would we be getting a match in prelims question? Least likely, no. Generally, we'll get statement-based questions. Maybe they'll ask, a low massive star will undergo supernova explosion. The answer will be no. So something like that. Very basic, they will ask. Clear? Okay, I'll play you two videos. Yes, smaller mass means greater lifetime. Vamshi, yes, smaller the mass, greater the lifetime. What is the reason behind fusion being directly proportional to mass of the star? So why fusion is directly proportional to mass of the star? So imagine you have a large cooker and you place somewhere close to one tumbler of dal inside. But if you have a large cooker, what you could do, you could place like somewhere close to 5 or 6 tumbler of dal inside and then cook. So basically, greater the mass, greater is the amount of elements present inside. So the matter present inside, it depends on the mass. So the larger the size, the greater is the reaction. When there is more element to fuse, there will be more fusion. Thermal energy will increase. It depends on the number of atoms present inside. Is it clear? Yeah. So I included captions in the slide, but it's not playing. So we have no other go than sticking to YouTube. ஸ்க்ரீன் ஷேரிங் போட்டிருக்கா? ஓகே. ம்.
About once every century, a massive star somewhere in our galaxy runs out of fuel. This happens after millions of years of heat and pressure have fused the star's hydrogen into heavier elements like helium, carbon, and nitrogen, all the way to iron. No longer able to produce sufficient energy to maintain its structure, it collapses under its own gravitational pressure and explodes in a supernova. The star shoots most of its innards into space, seeding the galaxy with heavy elements. But what this cataclysmic eruption leaves behind might be even more remarkable. A ball of matter so dense that atomic electrons collapse from their quantum orbits into the depths of atomic nuclei. The death of that star is the birth of a neutron star, one of the densest known objects in the universe, and a laboratory for the strange physics of supercondensed matter. But what is a neutron star? Think of a compact ball inside of which protons and electrons fuse into neutrons and form a frictionless liquid called a superfluid, surrounded by a crust. This material is incredibly dense, the equivalent of the mass of a fully loaded container ship squeezed into a human hair, or the mass of Mount Everest in a space of a sugar cube. Deeper in the crust, the neutron superfluid forms different phases that physicists call nuclear pasta, as it's squeezed from lasagna to spaghetti-like shapes. The massive precursors to neutron stars often spin. When they collapse, stars that are typically millions of kilometers wide compress down to neutron stars that are only about 25 kilometers across. But the original star's angular momentum is preserved. So for the same reason that a figure skater's spin accelerates when they bring in their arms, the neutron star spins much more rapidly than its parent. The fastest neutron star on record rotates over 700 times every second, which means that a point on its surface whirls through space at more than a fifth of the speed of light. Neutron stars also have the strongest magnetic field of any known object. This magnetic concentration forms vortexes that radiate beams from the magnetic poles. Since the poles aren't always aligned with the rotational axis of the star, the beams spin like lighthouse beacons, which appear to blink when viewed from Earth. We call those pulsars. The detection of one of these tantalizing flashing signals by astrophysicist Jocelyn Bell in 1967 was in fact the way we indirectly discovered neutron stars in the first place. An aging neutron star's furious rotation slows over a period of billions of years as it radiates away its energy in the form of electromagnetic and gravity waves. But not all neutron stars disappear so quietly. For example, we've observed binary systems where a neutron star co-orbits another star. A neutron star can feed on a lighter companion, gorging on its more loosely bound atmosphere before eventually collapsing cataclysmically into a black hole. While many stars exist as binary systems, only a small percentage of those end up as neutron star binaries, where two neutron stars circle each other in a waltz doomed to end as a merger. When they finally collide, they send gravity waves through space-time like ripples from a stone thrown into a calm lake. Einstein's theory of general relativity predicted this phenomenon over 100 years ago, but it wasn't directly verified until 2017, when gravitational wave observatories LIGO and Virgo observed a neutron star collision. Other telescopes picked up a burst of gamma rays and a flash of light, and later X-rays and radio signals, all from the same impact. That became the most studied event in the history of astronomy. It yielded a treasure trove of data that's helped pin down the speed of gravity, bolster important theories in astrophysics, and provide evidence for the origin of heavy elements like gold and platinum. Neutron stars haven't given up all their secrets yet. LIGO and Virgo are being upgraded to detect more collisions. That'll help us learn what else the spectacular demise of these dense, pulsating, spinning magnets can tell us about the universe. Continue exploring the mysteries of the universe with this playlist.
All right. So that's how it works. Right now we have neutron stars that we are observing. So there is a possibility that a neutron star can turn into black hole. If it's going to capture more energy from the nearby star, there is a possibility that it explodes and becomes a black hole by building mass. Good. So right now, lesser the mass, it becomes a neutron star. If it has greater mass, it becomes a black hole. Good. Next, I'll give you a basic introduction to black hole, and then we'll wind up. Clear? Any doubt till this? We feel a star falling down. Yeah, those are not stars. We have meteors and basically the asteroids. The rocky asteroids, once they enter the Earth's atmosphere, what will happen? They'll be ignited because of the friction. So before it reaches the Earth, it completely burns down. So we call it as meteors. There are two classifications. One is meteor, the other one is meteorite. Meteor and meteorite. If an asteroid is deviated from its path and once it enters into the Earth's atmosphere, it's called as meteor if it completely burns before reaching the ground. Good. If there is something left over before it reaches the ground and it falls on the ground making a large depression or a crater, you call it as meteorite. So both are rocky structures or asteroids. Completely burns, it's meteor. If it reaches the Earth's surface, it's called as meteorite. The last known meteoritic activity is a lot of like few thousand years before. We don't have a meteorite right now in any recent time. But meteors, it's frequent. If you just look at if you skywatch, we have meteor showers again and again on a constant basis. Clear? So those are not stars, those are meteorites. Okay, coming to the black hole. Question number 1. Okay, about comet. So we have solar system, and then we have Mercury, we have Venus, we have Mars. Sorry, we have Earth and Mars. Goes on till Neptune. Good. So all these planets, all these asteroids, what they do, they generally orbit around the sun. All the planets orbits around the sun, and also the asteroids. Good. These comets, they also orbit around the sun in a highly eccentric orbit. Good. So imagine something coming from outside the solar system, objects from outside the solar system orbiting the sun in an eccentric orbit. So these are called as comets. So comets are generally formed in Oort clouds. Repeat. The location is called as Oort clouds outside the Kuiper belt. There's something called as Oort cloud where comets are formed. So generally comets has ice content. So these comets, they'll be orbiting the sun. It has a highly eccentric orbit, which means it reaches much closer to sun and then it returns. So those are called as comets. So this contains ice, methane and everything. So if it is just rocky structure inside the solar system, you call it as asteroid. So imagine comet as asteroid from outer side. Clear? Yeah. So asteroids, they have only rocks, metals and everything. Generally there is no ice caps on asteroids. Wherein comets, since it's coming from the Oort cloud outside it's a trans-Neptunian object coming from outside the solar system, they generally have a lot of ice. So since the ice is melting when it's approaching the sun, what will happen is, it will create a long tail. The melting ice will create a long tail. So that's what we call as comet. Comet has the tail stars. So basically it's the water present inside that's melting and the methane that is burning and creating a huge tail. The nucleus part is the comet, and these are the melting part. When it approaches the sun, it will create a huge tail. These are comets. Clear? Coming to the next one, black holes. So true or false based question. Question number 1. Black holes can be seen with visible light. Black holes can be captured with visible light cameras. True or false? Just true or false model. Black holes can be captured with visible light cameras. False. Okay. An object cannot escape from black hole. True or false? I'll repeat the question, or we'll frame it this way. Light cannot escape from black hole. True or false? I'll repeat the statement once again. Light cannot escape from black hole. True or false? True. Okay. So basically black holes are regions with extremely high gravity. Good. So what will happen is even light cannot escape from it, which means if an object has to escape from black hole, it has to travel at a velocity greater than 3 into 10 power 8 meter per second. So imagine light travels in vacuum. The velocity of light in vacuum is 3 into 10 power 8 meter per second. For an object to escape from black hole, it should attain a velocity much higher than this. So that's called as a black hole. As I told you, it's a region of extremely high gravity, generally formed after a star explodes. You have to remember 3 things about the black hole. First thing is Schwarzschild radius, second thing is singularity, and the third one is event horizon. You can write the basic definition here. It's an astronomical object with extremely strong gravitational field. We'll complete this in another 2 or 3 minutes. Maybe we will need another 5 minutes extra. I think we'll be finishing around 4:35. So matter or radiation or anything that falls inside the black hole, it cannot escape. Have you heard of the term called as event horizon? Event horizon. See? So the black hole, the entire thing is not the black hole. Good. So black hole, it has the matter and everything compressed in a small space. So that's called as singularity. So we don't know what is present inside singularity. Till date, we don't know what is present inside singularity. So singularity basically means everything being extremely compressed into a single thing, that there is no proton, no neutron, no electron, nothing is there. Everything is compressed and stored in a single part. And what is that part? What is singularity is unknown till now. We don't know what is present in singularity, but all we know is there won't be proton, neutron, electrons or atoms that are existing individually, but everything will be compressed and they'll be stored in a single form. That's called a singularity. Good. So from singularity, any object or any star, anything that goes near the black hole, it will be engulfed. So this is called as point of no escape. So the maximum extent of the influence of black hole is called as event horizon. So event horizon is basically the outermost border of black hole's influence. So once the object crosses the event horizon, it cannot escape the black hole. I'll repeat it once again. Basically, once the object crosses the region called as event horizon, once it comes into the event horizon, it cannot escape outside. So to escape outside, it has to travel at a velocity greater than 3 into 10 power 8 meter per second, which means this is a border, or this is a region of no escape. Colloquially, it's a region of no return, or a point of no return. Once the object crosses this event horizon, it will be pulled by a black hole. Good. 2 terms. First is singularity. Second one is event horizon. Third one is Schwarzschild radius. So basically, the radius between the singularity and the event horizon. So this is called as Schwarzschild radius. Is it clear? Any doubt in this? You can write it down. So event horizon is the point of no return. It's not a physical state. It's basically a region, a space outside the black hole where an object cannot return. A point of no return is called as event horizon. Schwarzschild radius. I have a slide for it. The next slide is that. Don't worry, you can spell it again. So it's named behind the person who introduced the concept. This event horizon and the concepts are introduced by Stephen Hawking when he spoke about this Hawking radiation. And then the radius between the singularity and the event horizon was deduced by Schwarzschild. That's the astrophysicist's name. So we named it as Schwarzschild radius. Write down only the first line. Point of no return around the black hole is called as event horizon. Coming to the next part. Singularity, because all the matter, all the radiation, including light and everything, it will be squished and stored in a smaller point. That's called as singularity. The composition of singularity is unknown. I repeat, the composition of singularity is unknown to us. So it's a tiny volume with the enormous density. When I was showing the video about neutron star, it gave a basic example. What if you compress the entire Himalayan mountain, the Mount Everest, into a small sugar cube? So imagine compressing the Mount Himalayas, the Mount Everest, into a single cube of sugar. So it's that compressed. So element cannot exist, atom cannot exist, a proton, neutron, or electron, anything cannot exist. Everything will be squished into a smaller space. The process is called as spaghettification, technically. So like a spaghetti, it's stored in a single point. Good. The next one is Schwarzschild radius. So Schwarzschild radius or gravitational radius, the distance between singularity and event horizon. The distance between singularity and event horizon. Clear? Done? Audio play பண்றீங்களா? So we'll play a small video that goes up to 2 or 3 minutes and then we'll wind up. Until then, if you have any doubts about this, please drop a message. Play பண்ணலாமா?
Black holes are one of the strangest things in existence. They don't seem to make any sense at all. Where do they come from? And what happens if you fall into one? Stars are incredibly massive collections of mostly hydrogen atoms that collapse from enormous gas clouds under their own gravity. In their core, nuclear fusion crushes hydrogen atoms into helium, releasing a tremendous amount of energy. This energy, in the form of radiation, pushes against gravity, maintaining a delicate balance between the two forces. As long as there is fusion in the core, a star remains stable enough. But for stars with way more mass than our own Sun, the heat and pressure at the core allow them to fuse heavier elements until they reach iron. Unlike all the elements that went before, the fusion process that creates iron doesn't generate any energy. Iron builds up at the center of the star until it reaches a critical amount, and the balance between radiation and gravity is suddenly broken. The core collapses. Within a fraction of a second, the star implodes, moving at about a quarter of the speed of light, feeding even more mass into the core. It's at this very moment that all the heavier elements in the universe are created as the star dies in a supernova explosion. This produces either a neutron star, or if the star is massive enough, the entire mass of the core collapses into a black hole. If you looked at a black hole, what you'd really be seeing is the event horizon. Anything that crosses the event horizon needs to be traveling faster than the speed of light to escape. In other words, it's impossible. So we just see a black sphere reflecting nothing. But if the event horizon is the black part, what is the whole part of the black hole? The singularity. We're not sure what it is exactly. A singularity may be infinitely dense, meaning all its mass is concentrated into a single point in space with no surface or volume, or something completely different. Right now, we just don't know. It's like a dividing by zero error. By the way, black holes do not suck things up like a vacuum cleaner. If we were to swap the sun for an equally massive black hole, nothing much would change for Earth, except that we would freeze to death, of course.
All right. So the video gets more complicated after this. This is enough. So that's how black holes are formed. At event horizon, point of no escape. Schwarzschild radius is the distance between singularity to the event horizon. And singularity is basically what we don't know what is present inside, but everything is crushed and formed into a single point. That's called a singularity. So this much data is sufficient. Understanding is very much sufficient. So go through this basic before you come to the next class, because next we have to start with the recent current affairs with respect to all the supernova explosion and everything. Good. Try to read about the Big Bang theory, about the neutron stars, and about black hole and the life cycle of the star. Please go through it thoroughly once before coming to the next class. Is it clear? I won't be sending slides. I'll be sending you short notes. So after a few classes, I think in 7 or 8 classes, I'll be completing the topics given to me. So once it is over, I'll be compiling it and I'll be sending you a PDF document. Shouldn't supermassive star just before the stage of supernova explosion have much higher density at the core than the black hole? No. So black hole's density is unimaginably high. So that's what we are saying. So even though the mass keeps on increasing. Hubble's law slide, okay. I'll show you the Hubble's law. Any other doubt? So black hole is definitely more dense than Archana. Black hole is definitely more dense than supermassive stars. So supermassive stars, it's immediately after the red giant phase, which means the size may be large, but the density is lesser. Is it clear? So it's a fusion of remnants of explosion, I understand, but when it explodes, the core part is extremely compressed. So imagine the Big Bang when it started. Initially, it was in a highly compressed state. So like that, when the stars die out, the size keeps on decreasing. So which means smaller the size and the more the elements inside, it's going to be extremely compressed. So that's why you see neutron star has higher density, but compared to black hole, the density is much lower. Black hole is the region of highest density. So the star keeps on reducing the size. Smaller it gets, the remnants has more elements inside and it has more gripping gravity. Yeah. Imagine you have say 10 kilogram of rice. So 5 kilograms spills in an explosion and you have 5 kilogram left over. But you're going to store the 5 kilogram into a small dabba rather than a 5 kilogram bag. You're going to compress the leftover 5 kilogram of rice in an extremely small space inside a small dabba. What will happen? It will have more gravity. It works like that. So the analogy is for your basic understanding. It's not exactly the same way, but yeah. Smaller the size, more the gravity. Yeah. Any other doubt? Can we wind up? All right. So I'll see you in the next class. Thank you very much. Topics not needed for NCERT. Okay, give me 1 or 2 classes. I'll just give you a summary for physics, chemistry, and biology. So once we start biotech, I will be definitely saying what are the topics not to be covered under NCERT. Cynthia, you asked today, give me at least 1 week so that I could prepare the list of topics that could be ignored. Clear? Yeah, thank you. Thank you, everyone. Stop பண்ணிடலாம்.